Hello, virtual folks. Today, I recorded a video for you, which is much nicer than watching me live, and I understand that. It's been tough to find the time to do these videos, but I have some time. So you get to watch a video today, which is hopefully a much better format for you. We're going to continue on with 3.2. Last week, Thursday, I left you off right about here. And again, the next 4 sheets of this packet are really just, you know, like fact sheets or whatever you want to call them, like Wikipedia pages is I think the words I used on Thursday. So the first one here was on ionic compounds. And I pointed out one thing on Thursday, and I'm going to point it out again today because this is kind of a big deal when it comes to ionic compounds. The properties of ionic compounds are really unique. A lot of times when AP asks you questions of like identifying what type of solid you have, they're going to use these unique properties of these ionic compounds to help you answer the question. Okay, they'll say that, hey, this is a white crystalline solid and it's brittle and it doesn't conduct electricity in the solid form, but it does conduct electricity when it's dissolved in water. That's an ionic compound. So be aware that the conductivity of the ionic compounds and the brittleness of the ionic compounds are really what AP likes to use to like help you kind of identify or distinguish different types of solids. Okay? All right, so the next little fact page here is metals. I do want to point out the sketch that I have on this little fact sheet. Again, really what you have for metals is you have like the nucleus and the core electrons are representing like these red spheres, okay? And then these little black spheres are the valence electrons. So all of these, all the nuclei and core electrons are kind of packed in like the red spheres are here. And the valence electrons are free to flow and move all throughout the sample of the metal. That's the C of electrons, okay? C of mobile valence electrons, if I'm being more specific, right? So the idea here is that your metal bonding or your metal solid is very unique, and it conducts electricity and it conducts heat very well because of these free-flowing electrons. Some of the other properties here, they are malleable and ductile. Malleable means that you can like bend and mold and shape it, okay? Ductile is meaning you can like draw it into a wire, okay, which we use metal wires very often in our, wiring, obviously, sorry. They can be alloyed, which we'll talk about on the next slide, so let's go a little further. Again, there's different types of alloys, and again, there's a lot of good information in here, and you're more than welcome to read this and reference this as we do. But if you got some space, and I think you got a little bit of space, I'd recommend you draw these out. We've drawn these out previously, but there's the 2 types of alloys that you're really responsible for knowing. We have interstitial and we have substitutional. Substitutional alloys happen when you mix 2 metals with atoms almost the exact same size or very close in size. Okay, a good example of a substitutional alloy is brass, which I reference up above here. Okay, so for brass you have copper and you have zinc. And zinc and copper are almost the exact same size atom, so you get this alloy where one metal is just kind of replacing the spot of the original metal, so to speak, and they just blend in nicely and the spheres or the atoms are almost the same size. The other type of alloy is interstitial. This happens when you use 2 metals with varying sizes or very different sizes in their radius. So the example here is steel. Carbon is not a metal, but carbon is used and mixed with iron to create steel. But the interstitial part is what we're really focusing on, okay? So the big red spheres here are my iron atoms, and the little black ones are the carbon. Carbon atoms are much smaller than iron, and when we blend these 2 together, these little carbons just kind of tuck in to these little spaces, the interstices, or interstices, I don't know how to pronounce that. But it sticks in the middle, right? Here's the big irons, there's the little carbons, and this is a different type of alloy than this one. The interstitial one has a blend of larger and smaller atoms, and they pack together in a different way. The substitutional one is all about the same radius. All right, covalent networks. There's not much to point out here that I already haven't pointed out to you, but a couple of things up top that I really want to make a point of. Diamond and graphite, right? These are both carbon. Diamond is the 3-dimensional arrangement. Graphite is the 2-dimensional arrangement, so be aware of that. Again, diamond has It's a three-dimensional structure, nothing but covalent bonds, extremely strong substance, obviously. Graphite is a two-dimensional arrangement of carbon. It comes in sheets. So when you have millions and millions of sheets of graphite, that's how you write with your pencil, right? When you draw that pencil across a piece of paper, you are effectively just flaking off sheet after sheet after sheet of graphite. The other covalent networks that show up, I mean, really, AP uses like 3 or 4 examples when covalent network solids show up on the test. They're going to use either diamond, graphite, silicon dioxide, which is quartz or glass. This one's a little sneaky. And the reason why it's sneaky is because if you're not careful and you're going quick on a test and you see SiO2, you might accidentally say that this is a molecular solid. It kind of looks like it wants to be a molecular solid. But this is one you just flat out have to memorize. Excuse me. So silicon dioxide is glass or quartz. It is a covalent network solid. It is the one that you just must memorize because it's easy to screw up and call this thing a molecular solid. It isn't. The other one that sometimes shows up is the silicon carbide, the one on the very bottom here. It's more rare. Generally speaking, if AP is going to talk about covalent networks on that test, they're going to either bring up diamond, graphite, or silicon dioxide. So just kind of want you to make you aware of that because those are the 3 you really have to be on the lookout for to make sure you don't miss. Something else that comes up sometimes is the difference between diamond and graphite in terms of their properties. We talked about the difference between diamond and graphite in terms of their structure, diamond being a 3-dimensional covalent network, graphite being a 2-dimensional covalent network or like a sheet of carbons, okay? But they have very different properties. Diamond is rigid, hard, colorless. It's an insulator, it does not conduct, okay? Electricity or heat very well. Graphite, on the other hand, is very soft. Okay, you can take pencil lead and kind of, smush it and smash it a little bit. And the reason why you can is because it's those sheets, right? You're not actually breaking any covalent bonds. You're just breaking the London dispersion forces between those sheets. So it's very soft and it's actually slippery. Graphite is used as like a mechanical lubricant for machinery. You can use and like rub graphite. You can even do this at home. Take your pencil and darken a spot on a piece of paper really, really dark. And I mean just like, put tons and tons and tons of graphite on a piece of paper, rub your finger across it. It's slick, it's slippery. And if you have like a whole bunch of pencil on your fingers, right, or graphite on your fingers, it's the same thing. It's slippery. So it's that's very unique. It's different properties than diamond, obviously. Graphite's also black and it conducts electricity. This is unique as well. And I talked about graphene last week, Thursday. So these property differences between diamond and graphite sometimes also show up on an AP test. All right, molecular solids, there's not too much to talk about. Do be aware that the properties box here is maybe the best place to look in all of these sheets, but generally speaking, molecular solids have low molar masses, not always. Again, wax is my one go-to example that I've been using over and over and over. Wax is a molecular solid. And it has a very large molar mass, and that's probably why it is solid at room temperatures, because we have all of these London dispersion forces at play. Molecular solids, usually low melting points, usually low boiling points, non-conductive more often than not. Again, these are nonmetals making solid substances. Ice, we're very familiar with. Iodine is another example that I have up here. Okay, iodine is diatomic, so you'll notice that each of these little lattice points has 2 atoms of iodine bonded together. But again, each of these is going to have different intermolecular forces holding it together as well, right? So we have to analyze the molecular solids a little bit further in order to understand what the heck's going on. The high molar mass ones, again, stronger intermolecular forces due to the increased strength of the London dispersion forces. Again, mass goes up, electrons go up, size goes up, stronger London dispersion forces. So anyway, blah, 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 blah. I have a little bit about polymers down here and proteins down here. It really doesn't show up on the AP test, so don't worry too much. Okay, let's get into some of these questions on the very last page. I have 7 questions. I'm going to get through all of them today, all right? And some of these we've kind of talked about already in this video. Some of these we talked about last week, Thursday. Some of these we might need to revisit some of these little note sheets and try to figure out. But let's read the first one. Carbon graphite is used as a lubricant, whereas carbon diamond is used as an abrasive. Justify why these properties exist. Okay. Since you're watching the video, right, in class on Monday for the A group, I will be stopping and giving them a chance to answer. I would encourage you to do the same. If you stop the video, think about this. I'm not saying you have to give me the most perfect essay answer ever, but think about it, right? This is something that AP could totally ask you. So pause the video, give it a shot. All right, so carbon graphite and carbon diamond have different structures, right? We know that graphite, okay, is a two-dimensional sheet of carbons. Oh, can't spell. Okay. Between the sheets of these carbon layers, we have nothing but London dispersion forces. Okay. I should say two-dimensional sheets of carbon. Okay. I don't know what I'm doing. I don't want that S anymore. Whatever. Two-dimensional sheets of carbon between the layers. There are only London dispersion forces. That's it. And as a result, those layers can slide past each other really easily. It doesn't take a lot of energy to break the London dispersion forces. That's why graphite can be used as a mechanical lubricant. It just, that was my marker, they just slide past each other and very easily. It doesn't take a lot of energy, again, to break those London dispersion forces. For diamond, this is the three-dimensional one, right? This is a three-dimensional structure, or three-dimension, yeah, we'll say structure, of covalently bonded, I cannot spell again, covalently bonded carbon. All right, and when you have the three-dimensional version of this, man, oh man, diamond is one of the toughest, strongest substances known to man, especially naturally occurring, right? Naturally occurring substance. Diamond is very, very, very strong, and it has to do with the fact that it's a three-dimensional structure. Graphite, also very strong because, again, there's covalent bonds within those layers, but those layers can slide right past each other, and very different properties. That's what we're kind of getting at here. All right, number 2. Solid copper is an excellent conductor of electricity, but solid copper chloride is not. Justify why these properties exist. Same thing. Think about it, right? Don't just wait for me to answer that. That's completely, you don't learn things if you don't try things. That's just the absolute truth. Pause it. All right, I'm going to assume it's copper 2, because copper 2 is generally the more prevalent form of copper. I didn't specify. I really should have specified. This really should have a Roman numeral here of some sort. We'll go 2. Okay. But here's my formulas. Okay. Why does this conduct electricity and this does not? Well, they're different types of solids, right? The copper 2, or the copper over here, is a metallic solid. Metallic solids have a sea of electrons. And I'll say valence electrons, that's a better way of saying it. Okay? Conduct electricity very, very, very well. Copper chloride is an ionic solid. Okay? These only conduct electricity when dissolved. Oh, yeah. Dissolved. Oh, come on. in water or when molten. Okay, the term molten you've probably heard like, with like lava or magma. Molten is basically saying that something is liquid and really, really, really hot. So if you melt an ionic compound, it's going to be liquid and really, really hot. So that term molten applies here as well. So this is what's going on, right? The solid copper, it's a metal. It's a pure metal. It's metallic solid. It has a sea of valence electrons. Boom, it conducts electricity. Copper chloride, it's an ionic solid. Yes, there is copper in it, but that copper is in the form of copper ions. And our solid is that three-dimensional lattice structure of alternating ions. Ionic solids don't conduct electricity in their solid form. They only conduct when you dissolve them in water or when they're molten. That's why these properties are different. Magnesium oxide melts at a much higher temperature than sodium fluoride. Why? Now, this is actually almost the exact same type of question I was asking you last unit. I've just changed how I've phrased it. Last unit, I would ask you the question of, which of these has a greater lattice energy? Meaning, which of these has stronger ionic attractions or stronger ionic bonds? I'm kind of asking you the same darn thing. I'm just using the melting point, right? But we know that as the strength of those forces increases, the melting point goes up. So really, when I'm asking, hey, this one melts at a higher temp, why? I'm really just kind of saying, hey, this one has stronger ionic bonds. Why? Well, when we make comparisons between ionic compounds, right, we use Coulomb's law. Coulomb's law is going to help us explain this. I have magnesium oxide. I have sodium fluoride. Let's diversify our color palette. Okay, this is between magnesium ions that have a 2+ charge and oxide ions which have a 2- charge. This ionic compound is between sodium ions which have a 1+ charge and fluoride ions which have a 1- charge. Okay, this is pretty easy to explain, I think. Why does magnesium oxide have a much higher melting temperature? Well, based on Coulomb's law, the compound with the greater magnitude of charge will have a greater lattice energy. Therefore, so based on Coulomb's law, the compound with the greater magnitude of charge will have a greater lattice energy. Therefore, how do I want to phrase this? Magnesium oxide has stronger ionic bonds. Right? So it's all about it's all about how strong are the forces holding these things together. And we use Coulomb's law to help us analyze ionic compounds. Well, magnesium oxide with 2+, 2-, that's bigger charge, stronger force. Stronger force, it's much harder to melt. It all kind of ties in. Number 4. List 2 different ways that you can alter lithium chloride so that it would conduct electricity. All right, this is not bad. We kind of already talked about this, right? Lithium chloride is ionic. It's an ionic solid. Lithium is metal, chlorine is nonmetal. This is an ionic compound. So how can we force ionic compounds, or how can we get ionic compounds to conduct electricity? Well, we can dissolve it in water. That will work. The other way, melt it or make it molten. Okay? Here's the deal with those ionic compounds one more time. In the solid state, the ions are locked in place. Electricity can't flow when those charges are locked. If you put it in water and it dissolves, now the ions are free. The ions are actually free flowing throughout the entirety of that solution, throughout the water. Now, because those charged particles are moving and free to flow and move, the electricity can pass through or be carried through, traveled through. When it's molten or in a liquid state, it's the same thing. Now the ions are free to kind of move around and electricity can flow. Of steel and brass, which is more ductile? Ooh, fun. So this is the whole alloy thing, right? We have 2 different types of alloys that we're looking at. One is steel, which is an interstitial alloy, which means that the atoms of the metal or carbon in this instance are different sizes. So the carbons kind of tuck into those little spaces. Brass is a substitutional alloy, which uses copper and zinc, and the atoms are almost the exact same size, so they just kind of substitute or replace one another in that structure. Now, the term ductile means that you're like drawing your metal into a wire or making it into a wire and molding it, right? So let's go back to those pictures that I had right here. Nice. And think about this, because I think you can get the answer to this. Here's my interstitial. Here's my substitutional. Which of these do you think would be which of these would be easier to manipulate? Okay? It's got to be the substitutional alloy. The interstitial one is very, very strong and very rigid. When you fill these little gaps with other atoms, it's almost like it's kind of locking it in place. You're very familiar with steel. Steel's everywhere in our society, used in a lot of different things. Steel is extremely strong stuff, okay? It is tough to manipulate. Now, you're familiar with brass maybe too, if you've been hanging out at the Wausau West band room. But brass is more malleable and more ductile. Substitutional alloys, these atoms are a little more easy to allow to slide past one another, because that's really what we're doing, right? When I want to manipulate a metallic sample or change its shape or to draw it into a wire, I need these atoms to kind of move and slide past one another to make a new shape. In an interstitial alloy, that's tough, because these little carbons in this instance that kind of lock this in, they don't want to slide past each other anymore. It's like, you can almost think of it like there's like sand in the gears, right? These little carbons are like sand, and it makes it, it just doesn't want to move, okay? It's tougher, way more difficult to manipulate a metallic sample that's an interstitial alloy. Substitutional, these atoms aren't really locked into place. You can move them, you can shift them. It takes some energy, certainly, but it can happen. So let's write that out. Which of these is more ductile? We would absolutely expect that the substitutional alloy okay? Substitutional alloys are more ductile. Okay, why? Well, interstitial alloys I'm struggling, I'm sorry. Interstitial alloys have smaller atoms in between the larger atoms making them more rigid. Or you could say making it more difficult to manipulate that structure or move that structure or reshape that structure, something like that, right? The word rigid is kind of implying that. So, all right, number 6, you are given 2 unknown white solids. One is sugar, one is salt. What test could you do to determine the identity of the solid? And no, you cannot taste them. Okay, so generally, right, in science and chemistry in the lab, you're not eating things. It's not a good idea. I wouldn't recommend it. So let's take that out of the equation because, yes, I know that's the easiest answer and the one that most of you would have probably written down. I've got 2 white powders. I'm telling you that one's sugar, one's salt. Now, what can we do to prove which is which without eating them? Okay, well, think about it. Where are there differences in their properties? That's really what we want to utilize or take advantage of, right? Oh, how are they different? I've given you this answer a couple times, or there's more than one way to do this, by the way. But I think a great way would be to melt them. Or at least try, right? Sugar has a lower melting point than salt. Sorry for that random dot. Okay? Do a melt test. It's called a melting point test. That's a real test. You can totally do that. Sugar's going to melt first, salt would melt later. And I don't know, and again, it's going to take a lot to try to melt salt. It's pretty high melting point. So melting point, that's going to be a difference. Another way you could do this, and maybe you thought of this as well, is to check their conductivity. Sugar, molecular solids, sugar's a molecular solid, by the way, they don't conduct electricity at all, whether they are in their solid form or whether they are dissolved in water. So we could dissolve both of them. And check conductivity. Salt will conduct, well, when it's dissolved, right? And sugar will not. Okay, last one. Silicon melts at a much higher temperature than sulfur dioxide, which is higher than chlorine. Why? Let's justify these properties. What I'm really looking for here is, hey, here's 3 different things. They all melt at different temperatures. Let's think about what type of solid they would be. Okay? What type of solids are these? And that'll probably give us a pretty good indication as to why we have these differences in properties. So silicon, which I haven't really talked about for you guys, is one of these metalloids or semi-metals. Okay, it's right on that staircase. It's like sitting right on top of it. It's in the same family as carbon. That should maybe give us some indication of what's going on here. If we look at its temperature, it's really, really high. Okay, silicon forms a covalent network. Okay, much in the same way that carbon forms a covalent network. Now, if you said that this formed a metallic solid, that's kind of okay too. Silicon's weird, right? It's one of these semi-metals, so it's tough to kind of identify. But this, for our purposes, because it's in the same family as carbon, we'll say that this has a covalent network. Okay? And we know that covalent networks have extremely high melting points, and that's why we see that the silicon is at 1400 and the other two are literally gases at room temperature. Okay? So let's go to sulfur dioxide. Sulfur dioxide, what type of solid would this be? Well, it's nothing but nonmetals. This is a molecular solid. Okay. Well, it's molecular, but what kind of intermolecular forces would it have? That requires a little more thinking. We've done this Lewis diagram before, but I'll do it again. How many total valence electrons? We've got 18. Sulfur's in the middle. 1, 2, 2 bonds, I should say. That's 4 electrons. 14 electrons to go. I'm down to 2. There's my structure. It's not perfect. I really should fix it because that's not the Lewis diagram. If you look at formal charge, this ain't gonna work. Yeah. Don't mind my electron count. It's all gone. There's your structure. That's your appropriate Lewis diagram for sulfur dioxide. Coordination number is 3. I have 2 atoms and 1 lone pair around my sulfur. A coordination number of 3 would make a trigonal planar shape, but I don't have 3 atoms. I've got 2 atoms and a lone pair, so I get a bent shape. This is polar. And because it's polar, we know that sulfur dioxide is going to have dipole intermolecular forces. Let's go to the last example. We have chlorine, which is Cl2. Chlorine is a molecular solid. It's a molecule, right? It's only one element, but it is a molecule. We could do the Lewis diagram here, but it's very, very boring and very, very simple. What kind of intermolecular forces would this have? Nothing but London dispersion. Okay, it's nonpolar. So, why are these melting points so different? Well, they form different solids. The silicon is a covalent network, very high melting point. The sulfur dioxide is a molecular solid. The chlorine's a molecular solid. So that's all well and good. It's the same type, but let's go one step further and analyze it based off of their intermolecular forces. Sulfur dioxide, it's bent, it's polar, would have dipole-dipole. And chlorine, nonpolar, linear, would have London dispersion. Dipole-dipole forces are generally stronger than London dispersion. And as a result, we have covalent network, very high melting point, molecular solid with dipole-dipole, not high, but higher than the other molecule with nothing but London dispersion. Okay, that's all I have. Have a lovely day. We'll catch you tomorrow in live class. And yeah, if you need any help, don't be shy. Let me know. Your homework topic 1 is due tomorrow, by the way. It's really all the 3.1 stuff, not really the stuff that we've been talking about here. But, you know, if you need help, please don't be shy. Reach out. I'm happy to help you.